Folks, here we go. Read along, and I'll pause it at one particular place to make sure we're on the same page.
Italian physicist Enrico Fermi directed the first experiment that proved an atomic chain reaction could be self-sustaining in 1942 at the University of Chicago. Fermi describes the process of the experiment, which was named CP1, or Chicago Pile to 1, in the excerpt below. From Fermi's own story by Enrico Fermi, the year was 1939. A world war was about to start. The new possibilities appeared likely to be important, not only for peace, but also for war. A group of physicists in the United States, including Leo Szilard, Walter Zinn, now director of Argonne National Laboratory, Herbert Anderson, and myself, agreed privately to delay further publications of findings in this field. We were afraid these findings might help the Nazis. Our action, of course, represented a break with scientific tradition and was not taken lightly. Subsequently, when the government became interested in the atom bomb project, secrecy became compulsory. Here, it may be well to define what is meant by the chain reaction, which was to constitute our next objective in the search. For a method of utilizing atomic energy, an atomic chain reaction may be compared to the burning of a rubbish pile from spontaneous combustion. In such a fire, minute parts of the pile start to burn, and in turn ignite other tiny fragments. When sufficient numbers of these fractional parts are heated to the kindling points, the entire heap bursts into flames. A similar process takes place in an atomic pile, such as was constructed under the west stands of Stagfield at the University of Chicago in 1942. The pile itself was constructed of uranium, a material that is embedded in a matrix of graphite. With sufficient uranium in the pile, the few neutrons emitted in a single fission that may accidentally occur strike neighboring atoms, which in turn undergo fission and produce more neutrons. These bombard other atoms and so on at an increasing rate until the atomic fire is going full blast. The atomic pile is controlled and prevented from burning itself to complete destruction by cadmium rods, which absorb neutrons and stop the bombardment process. The same effect might be achieved by running a pipe of cold water through a rubbish heap. By keeping the temperature low, the pipe would prevent the spontaneous burning. The first atomic chain reaction experiment was designed to proceed at a slow rate. In this sense, it differed from the atomic bomb, which was designed to proceed at as fast a rate as was possible. Otherwise, the basic process is similar to that of the atomic bomb. The atomic chain reaction was the result of hard work by many hands and many heads. Arthur H. Compton, Walter Zinn, Herbert Anderson, Leo Szilard, Eugene Wigner, and many others worked directly on the problems at the University of Chicago. Very many experiments and calculations had to be performed. Finally, a plan was decided upon. 30 piles of less than the size necessary to establish a chain reaction were built and tested. Then the plans were made for the final test of a full-sized pile. The scene of this test at the University of Chicago would have been confusing to an outsider. If he could have eluded the security guards and gained admittance, he would have seen only what appeared to be a crude pile of black bricks and wooden timbers. All but one side of the pile was obscured by a balloon cloth envelope. As the pile grew toward its final shape during the days of preparation, the measurement performed many times A. Day indicated everything was going, if anything, a little bit better than predicted by calculations. Finally, the day came when we were ready to run the experiment. We gathered on a balcony about 10 feet above the floor of the large room in which the structure had been erected. Beneath us was a young scientist, George Weil, whose duty it was to handle the last control rod that was holding the reaction in check. Every precaution had been taken against an accident. There were 3 sets of control rods in the pile. One set was automatic. Another consisted of a heavily weighted emergency safety held by a rope. Walter Zinn was holding the rope, ready to release it at the least sign of trouble. The last rod left in the pile, which acted as starter, accelerator, and brake for the reaction, was the one handled by Weil. Since the experiment had never been tried before, a liquid control squad stood ready to flood the pile with cadmium salt solution in case the control rods failed. Before we began, we rehearsed the safety precautions carefully. Finally, it was time to remove the control rods. Slowly, Weil started to withdraw the main control rod. On the balcony, we watched the indicators which measured the neutron count and told us how rapidly the disintegration of the uranium atoms under their neutron bombardment was proceeding. At 11:35 a.m., the counters were clicking rapidly. Then, with a loud clap, the automatic control rods slammed home. The safety point had been set too low. It seemed a good time to eat lunch. During lunch,
So let's pause there for a second and make sure we all understand what's going on. So just to recap, they have a giant pile of uranium in graphite in a Chicago stadium. What's it covered in? What's keeping it safe between them and the pile? There is graphite, but what else?
The balloon.
Cadmium rods are going to keep the reaction from getting out of track, but the actual...
The balloon.
Right, it's covered by balloon cloth, which is like this really thin cloth used for like hot air balloons. So essentially, what stands between them and this giant pile of uranium is a large piece of silk. How are we feeling about these safety precautions here in the 21st century? Right. They had no idea. Remember, this was so early in the research. So what happened was they started the reaction, but the cadmium control rods slammed down and stopped the reaction before it even really got going. And that was because they set the safety point too low. They set the automatic trigger too low. And I think honestly, everyone was so nervous that when that happened, they were like, whew, okay, anybody want lunch? Let's break for lunch. Let's all get lunch, huh? See you in a couple minutes. Let's go get some lunch. So they really did break for lunch, and then they're going to start the reaction again in the afternoon. So here we go. We're going to read the last chunk, and this is where we really get into some applications and implications. So listen carefully.
It seemed a good time to eat lunch. During lunch, everyone was thinking about the experiment, but nobody talked much about it. At 2:30, Weil pulled out the control rod in a series of measured adjustments. Shortly after, the intensity shown by the indicators began to rise at a slow but ever-increasing rate. At this moment, we knew that the self-sustaining reaction was underway. The event was not spectacular. No fuses burned, no lights flashed. But to us, it meant that release of atomic energy on a large scale would be only a matter of time. The further development of atomic energy during the next 3 years of the war was, of course, focused on the main objective of producing an effective weapon. At the same time, we all hoped that with the end of the war, emphasis would be shifted decidedly from the weapon to the peaceful aspects of atomic energy. We hoped that perhaps the building of power plants, production of radioactive elements for science and medicine, would become the paramount objectives. Unfortunately, the end of the war did not bring brotherly love among nations. Secrecy that we thought was an unwelcome necessity of the war still appears to be an unwelcome necessity. The peaceful objectives must come second, although very considerable progress has been made also along those lines. The problems posed by this world situation are not for the scientist alone, but for all people to resolve. Perhaps a time will come when all scientific and technical progress will be hailed for the advantages that it may bring to man, and never feared on account of its destructive possibilities. So note, at the age of 53, Fermi passed away due to an untreatable stomach cancer. Despite his apprehensions about the potential dangers of working near the nuclear pile, he continued to do so, convinced that the advantages outweighed the risks to his personal safety. Sadly, 2 of his assistants, working in close proximity to the pile, later died of cancer as well.
So, ladies and gentlemen, we've got some very personal implications there, but we also have some broader implications for the planet. So what I'm going to do is give you the question again. Our practice expert panel question is, how was the first self-sustaining nuclear chain reaction achieved? Okay, I'm going to give you 60 seconds to think of your answer to that. Would you like the question again? All right. How was the first self-sustaining nuclear chain reaction achieved? Take 60 seconds to think about your answer, and then I'll tell you who's answering.